Hi, we are Group 1 and we are presenting our topic, compressor. First, what is compressor? A compressor is a mechanical device that increases the pressure of a gas by reducing its volume. At the compression, the low pressure gas is changed to high pressure gas. For example, in air compressor works by forcing air into a container, then it pressurizing it. For example po yung sa balloon, like we compress air into the balloon. Then kapag tinanggal natin siya sa pagkahawak, yung sa pinaka bunganga niya, it release high pressure energy or high pressure air. Next is the types of compressor. There are two types of compressor, which is positive displacement and dynamic. In positive displacement compressors, here are pressure is excited when air drawn in a chamber, then compressed by reducing the volume of the chamber. There are two classifications in positive displacement, the rotary and the reciprocating. In reciprocating, there is three classifications, the double acting, single acting, and diaphragm. And in rotary, there is 5 classification, which is lobe, screw, vane, scroll, and liquid ring. In dynamic compressor, air is accelerated to high velocity then pass through a diffuser. There is 2 classification in dynamic, which is axial and centrifugal. Reciprocating air compressors. Reciprocating air compressors have many uses in industry, including natural gas processing and delivery, chemical plants, and oil refineries. Sa reciprocating compressors po, it is widely used in various industry or in chemical application and even in refrigeration plants. Kasi po nagsusupply siya ng high pressure gas and gumagamit siya ng compressed natural gas. May tatlong classification reciprocating air compressor, which is the single acting, double acting, and diaphragm. This is the single acting compressor. In a single acting compressor, the air is compressed only on the upstroke of the piston inside the cylinder. In single acting, may disadvantage po siya because it is limited lang. Nakakapag-produce lang siya ng pressure ng about 10 bars or 145 psi. Here's the video of about how single acting works.
As the crankshaft turns, a piston reciprocates within the cylindrical housing. The inlet valve, also called suction valve, allows atmospheric air to enter the cylinder. This is done during a suction stroke of the cylinder. The outlet or discharge valve opens at high pressure during the compression strike. Air heats up when it is compressed. This is a problem of each compressor. The result is not only a less efficient compression cycle, but also to a real danger of explosion if any inflammatory substances, such as oil or lubricant, get contact with the overheated air and piston. Therefore, the compression of a single-stage compressor is limited to an output pressure of about 10 bars, or 145 psi.
Next is double-acting reciprocating air compressor. In double-acting reciprocating air compressor, it compresses the air in both the upstroke and the downstroke of the piston, doubling the capacity of a given cylinder size. Kung gusto nyo po maka-achieve ng high pressure, mas maganda pong gamitin yung two-stage or double-acting compressor. Here's the video of how double-acting reciprocating compressor works.
To achieve higher pressures, you would use a multi-step compressor. Here, a two-stage compressor is shown. The large piston builds the first stage. The air leaving the first stage can now be cooled before it enters into the second stage. With a two-stage compressor, you achieve pressures over 20 bars or 290 psi. Multi-stage compressors with high power also can use water cooling to avoid overheating.
Diaphragm compressor. A diaphragm compressor is a variant to the classic reciprocating compressor with backup and piston rings and rod seal. The compression of gas occurs by means of flexible membrane instead of an intake element. Here are the video of how diaphragm compressor work.
The diaphragm compressor belongs to the family of the piston compressors. Here, the suction chamber is sealed from the piston by a diaphragm. As an advantage, the compressed air in the compression chamber does not come in contact with the lubricated piston, and thus can be kept free of oil. The weak point of a diaphragm compressor, in general, is its membrane itself, since the elasticity is limited. You would use the diaphragm compressor, for example, in the food industry or to fill divers' bottles.
And that is the three classification of reciprocating air compressor.
Rotary screw compressor. A rotary screw compressor is a type of gas compressor, such as an air compressor that uses a rotary type positive displacement mechanism. Ito ang karaniwang ginagamit para mapalitan ng mga compressor ng piston kung saan mas kailangan ng hangin para tumaas ang pressure. Ipapakita namin kung paano nagwo-work ang rotary screw compressor.
During operation, the rotors turn and the spiral teeth mesh together, forming chambers between the rotors and the casing wall. Rotation causes the chambers to move from the suction or intake side to the compression or discharge side. These chambers are connected to the suction nozzle via ports. As the chambers enlarge, they are filled with gas flowing in through the nozzle. To understand the compression process better, let's look at an individual chamber. It enlarges, is filled with gas, and then closed by a circumferential edge in the casing. The rotors now transport the gas to the discharge side, where the chamber shrinks and the retained gas is compressed. Let's view the process again, this time from below. Once the gas is compressed, the chamber reaches another port connected to a discharge nozzle, and the gas flows out. In fact, all the chambers between the two rotors are being filled and emptied continuously. This means that with a screw compressor, the compression process is more or less ongoing. The design of a screw compressor combines the advantages of a positive displacement machine with those of a rotating machine, making this type of compressor suitable for a very wide range of applications and process gases.
Centrifugal compressor. Centrifugal compressors are used in small gas turbines and are the driven units in most gas turbines compressor trains. Ito ang video kung paano gumana ang centrifugal compressor.
A centrifugal compressor uses an impeller to draw in gas at the hub and accelerating it radially by centrifugal force through a circular flute housing. The housing acts as a diffuser that converts high-speed, low-pressure air leaving the impeller to high-pressure, low-speed air.
Next is axial compressor. An axial compressor is an integral to the design of large gas turbines such as jet engines, high-speed ship engines, and small-scale power station. Ang axial compressor ay isang gas compressor na kayang i-pressurize yung gas continuously, and it is a rotating airfoil-based compressor. Ito ang video kung paano gumalaw o nagwo-work ang axial compressor.
The inlet casing provides a smooth transition flow of air from the filters, through the silencers, and into the axial compressor. The inlet casing also provides access to the thrust bearing and the inlet journal bearing. Variable inlet guide vanes are located in the inlet casing directly in front of the first row of compressor blades. The vanes are used to regulate the amount of air entering the compressor. The circular operating ring actuates the guide vanes so that all vanes move in unison when opening or closing. Before each set of rotating blades is a set of stationary blades, or blade rings, that direct the air to the next set of rotating blades. The compressor blade rings have stationary airfoil-shaped vanes that direct the air to and from the rotating compressor blades. The rotating blades force the air into progressively smaller spaces as the air passes through the compressor. Heat of compression is generated in the air as it is passed through successive compressor stages. The compressor consists of 16 rows of individually removable rotating blades. Each blade is locked in place by a dovetail arrangement at the base of the blade. The rotor is made up of a bladed compressor spindle and a bladed turbine spindle that is bolted together to make one single shaft.
Compressor parts and its functions. These are the parts of single-acting compressor. Electric motor. Ito ang nagbibigay ng power sa compressor pump. Sa pamamagitan ng belt, kaya nito mag-transfer ng power papunta sa pump piston sa pamamagitan ng flywheel at crankshaft. Compressor pump. Dito ko na-compress ang hangin at nilalabas ito papunta sa kanyang receiver. Piston. Sa loob ng pump cylinder, kapag ang piston ay pababa, ibig sabihin, ang hangin ay pumapasok sa large cylinder sa pamamagitan ng filter at air intake valves. Ngunit kung ito naman ay pataas, ang piston ay kinakompress ang hangin sa large cylinder at ini-discharge naman ito papunta sa small cylinder sa pamamagitan ng intercooler tube. Receiver or tank. Ang main purpose nito ay pansamantalang paglagyan ng pressurized air. Nakakatulong din itong alisin ng tubig sa system sa pamamagitan ng pagpapalamig sa hangin. Pressure gauge. Dito natin makikita ang pressure level ng hangin na nasa loob ng compressor tank. Dito rin natin makikita kung ang air pressure ay tumataas o kaya naman ay bumababa. Pressure regulator. Dito natin makikita ang pressure setting ng air regulator. Ginawa ito upang makontrol ang flow ng hangin sa pamamagitan ng pag-adjust sa regulator setting. In-tank check valve. Ito ay matatagpuan natin sa pagitan ng compressor at ng air receiver tank. Ang main purpose nito ay para maging one-way lamang ang flow ng hangin. Ito ay upang maiwasan na hindi namamalik ang mga pressurized air pabalik na compressor. Drain valve. Lahat ng air compressor ay meron ito na matatagpuan natin sa ilalim ng air receiver. Ang main purpose nito ay para ma-drain natin ang mga naipon na tubig na nasa loob ng ating tank. Volute. Ang volute ay may dalawang function. Ito ay collection at ang diffusion. Kaya nito mag-collect and mag-transport ng fluid pababa sa ating system. Kaya din ito magpataas ng static pressure by converting kinetic energy to potential energy. Diffuser. Diffuser is an important element of a compressor. Its purpose is to reduce the velocity of the flow, leaving the impeller, resulting in an increase in pressure. Ported shroud. Ported shroud is a self-circulating casing treatment. Is widely used to delay the onset of the surge by enhancing the aerodynamic stability of the turbocharger compressor. Outlet pipe. A pipe with an opening which permits escape or release.
Theoretical analysis of gas compressor. The pressure, volume, and temperature relationship, where P1 V1 raised to n is equals to P2 V2 raised to n, and T2 over T1 is equals to P2 over P1 times raised to n minus 1 over n, and T2 minus over T1 is equals to V1 over V2 times raised to n minus 1, where n is a polytropic exponent. N is equals to 1 if isothermal compression, and N is equals to K if isentropic compression. To the capacity of compressor, or V. The capacity of the compressor is the actual volume of gas delivered considering suction, pressure, and temperature conditions. Its formula is volume 1 is equals to mRT1 over P1. The compressor work, or WC. In isentropic, it involves no cooling, and polytropic involves some cooling, and isothermal involves maximum cooling. The compression work for polytropic, or PV raised to n is equals to C is compression work is equals to n times P1 times B1 over n minus 1 times P2 over P1 is times raised to n minus 1 over n minus 1, or compressor work is equals to n times mass times constant value times temperature 1 over n minus 1 times P2 over P1 times raised to n minus 1 over n minus 1. In work of isentropic compression, or PV raised to K is equals to C, compression work is equals to K times P1 times B1 over K minus 1 times P2 over P1 times raised to K minus 1 over K minus 1, or compression work is equals to K times mRT over K minus 1 times P2 over P1 raised to K minus 1 over K minus 1. If enthalpies are given, adiabatic compression and neglecting kinetic and potential energy, the heat minus work in is equals to change of enthalpy plus change of kinetic energy plus change of potential energy, and work is equals to mass times H2 minus H1. The work for isothermal compression, or T is equals to C. Work compression is equals to P1 times B1 times ln P2 over P1, or work is equals to mRT1 ln P2 over P1. In compressor power, power is equals to volume flow rate times specific weight times enthalpy. In compressor efficiency, it is defined as the ratio of compressor power to shaft brake power. Compressor efficiency is equals to compressor power over brake power times 100%. In centrifugal, there is 70 to 85%. In high-speed reciprocating, there is 72 to 85%. And in low-speed reciprocating, there is 75 to 90%. And in rotary screw, there is 65 to 75%.
Problem solving number 1. A single-stage double-acting air compressor of 150 kilowatt power takes air in at 16 bar and delivers at 6 bar. The compression follows the law of PB 1.35 is equal to C. The compressor runs at 160 RPM with average piston speed of 150 meter per minute. Determine the size of the cylinder. For the given data, power is 150 kilowatt. Piston speed is equal to 150 meter per minute. Speed is equal to 160 RPM. Converting to RPS, 160 divided by 60 is equal to 2.7 RPS. Pressure or P1 is equal to 1 bar or 100 kilonewton per meter squared. Pressure or P2 is equal to 600 bar or 600 kilonewton per meter squared. PB 1.35 is equal to C. N is equal to 1.35. Hence, it is a polytropic process. To find the size of the cylinder, it is given that 2ln is equal to 2.5 meter per second. Cross multiplication to get the value of L. L is equal to 225 over 2 times 2.7. L is equal to 0.4629 meter. Since B1 is equal to Bs is equal to N over 4 D squared times L. Then substitute V1 is equal to Vs is equal to N over 4 D squared times 1.4629. V1 is equal to 0.3635 D squared. We know that the power is equal to 2 times W times N for double acting or for polytropic process work done. Work is equal to work W N over N minus 1 times P1 V1 times the parenthesis of P2 over P1 raised to N minus 1 over N minus 1. Then substitute work is equal to 1.3 over 1.35 minus 1 times 100 times 0.3635 D squared times the parenthesis of 6 raised to 1.35 minus 1 over 1.35 minus 1. The work is equal to 82.899 D squared. For the power formula, 2 times work times N. Substitute 150 is equal to 2 times 82.899 D squared times 27. Then transpose or cross multiplication, D squared is equal to 0.3350 or D is equal to 0.57 meter. Problem solving number 2. A single stage acting reciprocating air compressor is required to handle 30 cubic meter of free air per hour measured at 1 bar. The delivery pressure is 6.5 bar and the speed is 450 RPM. Volumetric efficiency of 75%, an isothermal efficiency of 76%, and mechanical efficiency of 80%. Find the indicated mean effective pressure and power required the compressor. For the given data, volume or B1 is equal to 30 meters squared. Pressure or P1 is equal to 1 bar. P2 is equal to 6.5. Speed N is equal to 450 RPM. Volumetric efficiency is equal to NV 75%. Isothermal efficiency is Ni equal to 76%. And mechanical efficiency Nm is equal to 80%. To find the indicated mean effective pressure, the power required to drive the compressor. Solution. Indicated mean effective pressure, we know that the isothermal work done. Therefore, the power required to drive the compressor is equal to 2.56 kilowatt. resulting indicated mean effective pressure PM is equal to 184.5 kilonewton meter squared. The power required to drive the compressor is equal to 2.56 kilowatt. Solution. Indicated mean effective pressure, we know that the isothermal work done is equal to 2.3 B1 P1 log parenthesis of B2 over B1 is equal to 2.3 times 10 raised to 5 times 3 log the parenthesis of 6.5 over 1 is equal to 5,609 times 10 raised to 3 joule per hour. And indicated work done is equal to isothermal work done over isothermal efficiency. Indicated work done is equal to 7,380 kilojoule per hour. We know that the sweep volume of piston or Vs is equal to volume of free air over volumetric efficiency, 30 over 0.75. Sweep volume of piston is equal to 40 cubic meter per hour. For indicated mean effective pressure PM, indicated work done over sweep volume is 7,380 kilojoule per hour over sweep volume 40. The indicated mean effective pressure is equal to 184.5 kilojoule per cubic meter or 184.5 kilonewton per meter squared. The power required to drive the compressor. We know that the work done by the compressor is equal to indicated work done over mechanical efficiency, 7,380 over 0.05 is equal to 9,225 kilojoule per hour. Problem solving number 3. A two-stage single acting air compressor compress air to 20 bar. The air enters the low pressure cylinder at 1 bar and 27 degrees Celsius and leave it at 4.7 bar. The air enters the high pressure cylinder at 4.5 bar and 27 degrees Celsius. The size of the low pressure cylinder is 400 mm diameter and 500 mm stroke. The clearance volume in both cylinders is 4% of the respective stroke volume. The compressor runs at 200 rpm, taking index of compression and expansion in the two cylinder as 1.3. Estimate 1. Find the indicated power required to run the compressor and 2. The heat rejected in the intercooler per minute. For the given data, pressure or P4 is equal to 20 bar, pressure P1 is equal to 1 bar or 1 times 105 Newton per meter squared. Temperature T1 is equal to 27 degrees Celsius, converting to Kelvin. 27 plus 273 is equal to 300 Kelvin. For pressure P2, 4.7 bar. Pressure P3 is equal to 4.5 bar. Temperature or T3 is equal to 27 degrees Celsius, converting to Kelvin. 27 plus 173 is equal to 300 Kelvin. And diameter D1, 400 mm or 0.4 meter. Stroke L1 is equal to 500 mm or 0.5 meter. For K is equal to 0.04. N is equal to 200 rpm. N is equal to 1.3 or expansion in the two cylinder. To find indicated power required to run the compressor. Solution, we know that the sweep volume of the low pressure cylinder is equal to 2,000 43.5 times 103 joule per minute is equal to 2034.4.5 kilojoule per minute. BS1 is equal to N over 4 D1 raised to 2 L times L1 is equal to N over 4 times 0.4 squared times 0.5 is equal to 0.06284 cubic meter. The volumetric efficiency, or NV, is equal to 1 plus K minus K times P2 over P1 raised to 1 over N is equal to 1 plus 0.04 minus 0.04 times the parenthesis of 4.7 over 1 raised to 1 over 1.3. And the volumetric efficiency is equal to 0.9085 or 90.85%. For the volume of air sucked by air pressure compressor, V1 is equal to Vs1 times NV is equal, substitute the value, is equal to 0.06284 times 0.905 is equal to 0.0571 cubic meter per stroke is equal to 0.0571 times NW is equal to 0.0571 times 200 is equal to 1 or is equal to 11.42 cubic meter per minute. And for volume of air sucked by high pressure compressor, V3 is equal to P1 V1 all over P3. Substitute the value, 1 times 11.42 over 4.5 is equal to the air sucked by high pressure compressor is 2.54 cubic meter per minute. We know that the indicated power work done by low pressure compressor, WL, is equal to N over 1 N minus 1 times P1 V1 times the parenthesis of P2 over P1 raised to N minus 1 over N minus 1. Substitute the value, WL is equal to N 1.3 over 1.3 minus 1 times 1 times 10 raised to 5 times 11.42 times the parenthesis of 4.7 over 1 raised to 13 minus 1 over 1.3 minus 1. WL is equal to 2123.3 times 10 raised to 3 joule per minute, or 2123.3 kilojoule per minute. And for indicated work done by HP compressor or high pressure compressor, WH is equal to N over N minus 1 P3V times V3 times the parenthesis of P4 over P3 raised to N minus 1 over N minus 1. WH is, substitute the value, WH is equal to 1.3 over 1.3 minus 1 times 4.5 times 10 raised to 5 times 2.54 times the parenthesis of 4.20 over 4.5 raised to 23, 1.3 minus 1 over 1.3 minus 1. WH is equal to 2043.5 times 10 raised to 3 joule per minute, or 2034.5 kilojoule per minute. For the total indicated work done by the compressor, work is equal to WL plus WH is equal to 2123.3 plus 2034.5 is equal to 4157.8 kilojoule per minute. Indicated power required to run The compressor is equal to 4157.8 divided by 60 is 69.3 kilowatt. Problem solving number 4. A sling psychometer gives reading of 25 degrees Celsius dry bulb temperature, 15 degrees Celsius wet bulb temperature. The barometer indicates 760 mm of Hg, assuming partial pressure of the vapor as 10 mm of Hg. Determine 1. Specific humidity, 2. And saturation ratio. For the given data, dry bulb temperature TD is equal to 25 degrees Celsius. Wet bulb temperature TW is equal to 15 degrees Celsius. For barometric pressure, PB is equal to 760 mm of Hg. Partial pressure PV is equal to 10 mm of Hg. To find the specific humidity and saturation ratio. Solution, we know that specific humidity W is equal to 0.622 PV over PV minus PV. Substitute the value of 0.622 times 10 all over 760 minus 10. The specific humidity is equal to 0.0083 kilogram per kilogram of dry air. For saturation ratio, from steam table corresponding to dry bulb temperature TD is equal to 25 degrees Celsius, we find the partial pressure PS is equal to 0.03166 bar. So, saturation ratio is equal to 0.03166 all over 0.00133. Saturation ratio is equal to 23.8 mm of Hg. We know that the saturation ratio is equal to PV times the parenthesis of PB minus PS all over PS times the parenthesis of PB minus PV. Substitute the value 10 is 10 times the parenthesis of 760 minus 23.8 all over 23.8 times 760 minus 10. The saturation ratio is equal to 0.4. A two-stage single-acting air compressor compress air to 20 bar. The air enters the low-pressure cylinder at 1 bar and 27 degrees Celsius and leave it at 4.7 bar. The air enters the high-pressure cylinder at 4.5 bar and 27 degrees Celsius. The size of the low-pressure cylinder is 400 mm diameter and 500 mm stroke. The clearance volume in both cylinders is 4% of the respective stroke volume. The compressor runs at 200 rpm, taking index of compression and expansion in the two cylinder as 1.3. Estimate 1. Find the indicated power required to run the compressor and 2. The heat rejected in the intercooler per minute. For the given data, pressure or P4 is equal to 20 bar, pressure P1 is equal to 1 bar or 1 times 105 Newton per meter square. Temperature T1 is equal to 27 degrees Celsius, converting to Kelvin. 27 plus 273 is equal to 300 Kelvin. For pressure P2, 4.7 bar. Pressure P3 is equal to 4.5 bar. Temperature of T3 is equal to 27 degrees Celsius. Converting to Kelvin, 27 plus 173 is equal to 300 Kelvin. And diameter D1 400 mm or 0.4 meter. Stroke L1 is equal to 500 mm or 0.5 meter for K is equal to 0.04. N is equal to 200 RPM. N is equal to 1.3 or expansion in the two cylinder. To find indicated power required to run the compressor. Solution, we know that the sweep volume of the low pressure cylinder is equal to 2043.5 times 103 joule per minute is equal to 2034.4.5 kilojoule per minute. We know the sweep volume of the LP cylinder. BS1 is equal to N over 4 D1 raised to 2 L times L1 is equal to N over 4 times 0.4 squared times 0.5 is equal to 0.06284 cubic meter. The volumetric efficiency or NV is equal to 1 plus K minus K times P2 over P1 raised to 1 over N is equal to 1 plus 0.04 minus 0.04 times the parenthesis of 4.7 over 1 raised to 1 over 1.3. And the volumetric efficiency is equal to 0.9085 or 90.85%. For the volume of air sucked by air pressure compressor, V1 is equal to VS1 times NV is equal, substitute the value is equal to 0.06284 times 0.905 is equal to 0.0571 cubic meter per stroke is equal to 0.0571 times NW is equal to 0.0571 times 200 is equal to 1 or is equal to 11.42 cubic meter per minute. And for volume of air sucked by high pressure compressor, V3 is equal to P1 V1 all over P3. Substitute the value 1 times 11.42 over 4.5 is equal to the air sucked by high pressure compressor is 2.54 cubic meter per minute. We know that the indicated power work done by low pressure compressor WL is equal to N over 1 N minus 1 times P1 V1 times the parenthesis of P2 over P1 raised to N minus 1 over N minus 1. Substitute the value. WL is equal to N 1.3 over 1.3 minus 1 times 1 times 10 raised to 5 times 11.42 times the parenthesis of 4.7 over 1 raised to 13 minus 1 over 1.3 minus 1. WL is equal to 2123.3 times 10 raised to 3 joule per minute or 2123.3 kilojoule per minute. And for indicated work done by HP compressor or high pressure compressor, WH is equal to N over N minus 1 P3V times V3 times the parenthesis of P4 over P3 raised to N minus 1 over N minus 1. WH is substitute the value. WH is equal to 1.3 over 1.3 minus 1 times 4.5 times 10 raised to 5 times 2 0.54 times the parenthesis of 4.20 over 4.5 raised to 1.3 minus 1 over 1.3 minus 1. WH is equal to 2043.5 times 10 raised to 3 joule per minute, or 2034.5 kilojoule per minute. For the total indicated work done by the compressor, work is equal to WL plus WH is equal to 2123.3 plus 2034.5 is equal to 4157.8 kilojoule per minute. Indicated power required to run the compressor is equal to 4157.8 divided by 60 is 69.3 kilowatt